Alright, welcome to another AQA A-level chemistry video. Today I'm going to be making a video on DNA. In A-level chemistry, DNA isn't a topic that comes up quite a lot. The depth of understanding isn't too great. All you need to just know is the structure of DNA, structure of DNA, of course, but know that DNA is a polynucleotide chain and is made of subunits of obviously mononucleotides or nucleotides, and that there are 4 different types of nitrogenous bases. You don't need to know the structure of those bases. Just know that because they're given to you in your data booklet, but you do need to know how those bases bond together. So if you know about the hydrogen bonding, so yeah, I mean, knowing how those bases bond together, you have to actually in your exam you might get a 5-mark question. This might be the only question on DNA they might actually ask you, but they might ask you some others. But it's mostly about how to draw the structure of two bases bonded together. And it may seem really difficult, but if you know from basic biology that adenine binds to thymine, cytosine bonds to guanine, you already have a head start in that sense, and you'd be quite easy to see how they would bond together. Apart from that, knowing how there's different types of bonds, just phosphoester bonds, or phosphodiester bonds, really, that if you know from A-level chemistry. But some of the things you know from GCSE chemistry, if you didn't do A-level chemistry, A-level biology, sorry, there's some things from here that if you do A-level biology, it really helps. But there's some things here from GCSE biology that should help you out enough to understand this topic. But yeah, I'm gonna get straight into it. So, DNA is essential to pass on genetic information in living organisms. It provides the necessary code in cell replication and protein synthesis. So, basic structure of DNA. A strand of DNA is a polymer of nucleotides. In other words, a chain of nucleotides, which is just a polynucleotide chain. Nucleotides are made up of deoxyribose sugar molecule, which is just a pentose sugar. Well, be specific about this point here, right? So, make sure to say specifically a deoxyribose sugar and not a ribose sugar, because a deoxyribose sugar is specifically only for DNA, and a ribose sugar is for RNA. And don't just say pentose sugar, because though it's not wrong, it's not specific enough. Because technically a ribose sugar is a pentose sugar, but it's not. It's only in RNA. It's not in DNA. Whereas deoxyribose sugar is a pentose sugar, but specifically for DNA. I don't believe you need to know anything about RNA when it comes to A-level chemistry. That's more for A-level biology. So, for nucleotides, it means up of a deoxyribose sugar molecule attached to a phosphate ion and a complementary nitrogenous base pair, as shown below. So if you got confused between, if you couldn't imagine in your head, for someone that doesn't do biology, what this structure would look like, you know, a deoxyribose sugar that's bonded to both a phosphate ion and a complementary nitrogenous base pair, I'll show you an example below so you can understand what I'm trying to say to you. Because I can understand this, how saying all these words together, it kind of makes it hard for you to click how that structure would look like. Don't worry, I've got an example for you. But in biology terms, 5-3 is used, which comes from the chemistry understanding of nomenclature. So if you do A-level biology, you know about 5' to 3', but obviously that understanding comes from nomenclature. So the nitrogenous base is bonded to carbon 1 on the deoxyribose sugar, and the phosphate ion group is bonded to carbon 5 on the deoxyribose, forming a phosphoester bond. When you have a dinucleotide forming, of course, the phosphate group from another nucleotide forms a phosphoester bond with carbon 3 of the first nucleotide, hence a 5, we call it 5' and 3', but 5-3 phosphodiester bond linkage. Again, I know this is a bit, even this little part here where I kind of explained it, it may confuse you. Don't worry, I'll show you exactly what I mean when I go through my example, and you make it much more sense once you understand. It's just, if you understand basic nomenclature, once you see the side groups, I'm just talking about the carbon 1 and carbon 5. I'm just telling you where these side groups are bonded to, and it makes sense once you see it. So nucleotides join together to produce a chain of condensation reactions between phosphate and a deoxyribose molecule, which is just a phospho, as I say here, 5-3 phosphodiester bond linkage. Right, so this is what a nucleotide looks like, right? So this is what a nucleotide looks like. So you have your nitrogenous base, your sorry, I want to kind of went through that here. We'll go through what I mean here later on. So this is what your nucleotide looks like. You have your nitrogenous base, your deoxyribose sugar, and your phosphate sugar, right? The reason why it's called a nitrogenous base, of course, is because it has nitrogen, multiple types of examples of secondary and tertiary nitrogens. So hence why that's there. Your deoxyribose sugar and your phosphate group. So I'm going to kind of isolate them out to make it a bit easier for people to get to grips. So I have actually one of that there. Let's move it more here. Have our nucleobase. In this case, it is adenine. The example I have here is of adenine, but this concept applies to any of the nucleotide bases. I'm just using this one as an example here. That was kind of weird. We have our deoxyribose sugar. And then we have our phosphate group. Right, now, so I'm just going to go, actually, I should probably just highlight what I mean here. So, our nucleobase is everything from here to there. This is our nucleobase. Our deoxyribose is everything from here, come around here, and then our phosphate group is here. Now, was that before I mentioned I mentioned about the 5-3? I talked about here, right? The 5-3 phosphodiester bonds, and nitrogen is being bonded to carbon 1. So let's say I'll show you exactly what I mean. So the sorry the nucleobase and our phosphate group, consider them like side groups, and consider the deoxyribose as being the main group. Obviously, our phosphate group doesn't have any carbons in it, so we can't give that the normal nomenclature: carbon 1, carbon 2, carbon 3. And our nucleobase changes all the time. It's not constant. It could be in this case it's adenine, but it could be thymine, cytosine, guanine. And technically, if we're doing chemical understanding to it, in RNA it could also be uracil, but you don't have to worry about uracil or that. Just know adenine, cytosine, thymine, and guanine, right? So the only way we can actually give a UPAC on naming by this is by you going by the constant here, which is always the deoxyribose sugar. So what I mean by this is said that this is the main, consider that the nucleobase as being the main side group, because that's the one that changes, that's the one that's affecting that's what gives the name of the nucleotide, right? That's what affects the type of nucleotide that you have, and that's the because in some aspects you can consider your nucleobase as an R group, right? You can consider it like an R group, and that's what determines the naming or the type of nucleotide that you have. Right, so we always said that because it's the main one here, this is on carbon 1. And if we're going to go right like this right here, we're going to go say 1, that's carbon 1, this is carbon 2, this is carbon 3, that's carbon 4, and this would be here carbon 5. Right, so we said the base is on, the nitrogenous base is on carbon 1, and our phosphate group is bonded to carbon 5. Now, what I said here, so you can also have 5-3 phosphodiester bond. So here is a phosphoester bond, but it's possible when nucleotides on the same strand bond together to form a polynucleotide chain. I'm not talking about a double strand here. I'm not talking about when the bases form hydrogen bonds together and you're forming 2 strands. I'm talking about on the same strand. How they actually bond together is that a phosphate group, say let's call this whole nucleotide here nucleotide 1, right? If I had a nucleotide 2, the phosphate group on nucleotide 2 would bond to carbon 3, or not bond to carbon 3, it would form a phosphoester bond with the alcohol group here. So it would form a phosphoester group with the alcohol group here, forming, so it binds so it reacts with the hydroxyl group here, which is also bonded to carbon 3, forming a phosphoester bond here. And once that happens, you have a 5. You then have a whole nucleotide then that's bonded to another nucleotide. That forms your dinucleotide chain, right? So just to make it, I'll say it again, so in case you got it confused here. If, say this is nucleotide 1, if nucleotide 2 wanted to bind to this to form a dinucleotide, the phosphate group on nucleotide 2 would bind to, would react to the hydroxyl group on carbon 3 on nucleotide 1, forming a phosphoester bond. Hence, now you have a 5-3 phosphodiester bond. If that made any sense, I can say that here, but let me show you an example. Hopefully that made sense, and this is an example of what I mean here, right? So this is carbon 5. So say this is like one of the nucleotides that we have here. It's bonded to the nitrogenous base here, or just know about that. And this is nucleotide 1. This is nucleotide. So we'll call this we'll call this nucleotide 1 because I here and I plus 1. So let's call this nucleotide 1, and we'll call this nucleotide 2, right? So we already know from here that the nucleotide is the phosphate group bonded to carbon 5, and it's obviously the same thing here, but it can also form a bond with the ester group, forming an ester here, a phosphodiester bond here with carbon 3. So on the carbon 3 of nucleotide 1. So nucleotide 1, the carbon 3 on nucleotide 1 can form a phosphoester bond with the phosphate group on another nucleotide, and hence you got 5-3, 5-3, and it will do the same thing as it goes down here. It's got 5-3, 5-3, and then it'll be as you go down here 5-3, so on, so on, so on, and so on, and that's what kind of creates it kind of twist. That's when you look at DNA, it kind of twists, and that's because of it's to do with the hydrogen bonding between the bases, but this is kind of why it's kind of got that backbone shape, and it's not a straight line. It kind of dents in a little bit. It's more the twisting aspect of it. The helical structure is more to do with the bonding between the nitrogenous bases. But just to understand that it's why it's called a phosphodiester bond, is because of that 5-3 bonding as it goes. Hopefully you understand what that means. If you didn't understand what I was trying to say here, leave a comment in the video, and I'll explain to you what I'll try and explain in a way that makes sense. But hopefully it's made sense. 5-3, 5-3, yeah, and so on. Right. So there's 4 different types of bases: adenine, thymine, cytosine, guanine. And here are the examples here. So that's adenine, that's thymine, that's cytosine, that's guanine. I'm not going to spend too much time talking about this because it's given to you in the data booklet. What you actually need to know is how they bond together. So if you know that, first of all, you didn't know already that there's only these nitrogen bases are specifically complementary to one another. So adenine can't bond to guanine, and cytosine can't bond to thymine. Adenine only bonds to thymine, cytosine only bonds to guanine. And the reason for that is that I'll show you why, because they only form a certain number of bonds. Because there's a reason for that. Because adenine thymine is notoriously known as a double bond. It forms 2 bonds, and I'll show you how those double bonds form. Cytosine guanine is a triple bond, and I'll show you how those triple bonds form. And that's how they're able to be complementary to one another, because they only form a certain number of bonds. So double helix in DNA. So DNA has a double helix structure constructed from 2 anti-parallel nucleotide chains. By the way, if you're talking about this here, I know it's not related to chemistry here. If you do A-level biology, this is something that you could talk about in your essay. By the way, I know it's not. I know this is meant to be a chemistry video, but if you ever want to talk about if they ever give you a question about structure or how they're related, you can talk about this here in the bonding here. It's got double bonds here, triple bonds, and that's specific. But this I'll go into chemistry because I know people look and say I only do chemistry. I'll make sure to get onto that. So DNA is a double helix structure constructed from two antiparallel nucleotide chains. The antiparallel nature is due to the phosphodiester bonds from 5' to 3', or if you want to talk about the prime part, you can just say 5 to 3. And the reason why it says it's considered to be anti-parallel, because on one side of the chain, if you're just going down this side of the chain, as I said before, I'm not talking about both of the nucleotides joined together here in this one example, but say that they were. Say if we're talking about two parallel chains, because DNA is a double nucleotide strand, a double polynucleotide chain. Say this is on one side of the chain, it goes from 5 to 3, 5 to 3, 5 to 3. On the other side of the strand, it'll be flipped. It'll be opposite. It will look like 3 to 5, 3 to 5, 3 to 5 as you're going down the strand, and that's because it's got an anti-parallel nature to it. So one side will be going like this, another side will be going like that. But when you look at it, it looks like 5 to 3, 5 to 3, 5 to 3. But because it's flipped on the other side, it'll read 3 to 5, 3 to 5, 3 to 5. If you're looking at it going up this way, it look like 5 to 3, 5 to 5, 5 to 3. But just to know that they are flipped and it gets anti-parallel, hence why it's called anti-parallel. So 5 to 3 on one side and 3 to 5 in the other direction, hence anti-parallel. So the double helix is held together by hydrogen bonding between the complementary base pairs. By the way, not everything in this video that I've talked about is going to come from exam. I'm just giving you as much information as possible so you can get understanding of it, so that when you get the 5-mark question, you can do it in 2 minutes because you know everything that you need to know about the question and everything makes sense to you. There's no confusion. So the double helix is held together by hydrogen bonding between the complementary base pairs, A with T and vice versa, and C with G, vice versa. So when I say vice versa, I mean T with A, because depending on what side they are. But adenine bonds to thymine, or thymine bonds to adenine, cytosine bonds with guanine, guanine bonds to cytosine. Same thing, right? So base pairing. So below shows the two complementary base pairs coupled together through hydrogen bonding. So C, a cytosine guanine forms 3 hydrogen bonds, and adenine thymine forms 2 hydrogen bonds. The double helix structure itself structures itself based around these hydrogen bonds. So it twists and turns until the hydrogen bonds are in the correct placement. So it twists and turns till it has the correct alignment and distance between the two bases. That's all it's just saying there. It's pretty much all this twisting, turning. The double helix structure is the double helix structure in itself is just based around the fact that they're two complementary shapes, or two complementary molecules, and because of that, they're complementary because of the type of bonding that they have, and that bonding is, as I'll show you an example of it before now, determines that bonding determines its alignment, its a distance between the two molecules, and hence it will have an overall effect on the shape of the DNA molecule. Now, this is guanine and cytosine. Hence, when we say cytosine and guanine, this is why it's got triple bond here. It's got 3 hydrogen bonds. Now you need to be able to see this. In the exam, they're not going to give this to you. They'll give you the structure of guanine. They give you the structure of cytosine. They won't rotate it for you. You just need to see that, okay, cytosine and guanine. So cytosine that's an electronegative group, that's an electronegative group, that's a partially positive group. Where has that got the same, what's the complementary to that? So if this is electronegative, if this is the partially negative, partially positive, I need to find partially positive, partially negative. And where's that an example of here? We've got partially positive, partially negative, partially positive. So it can go from here. Does that work? Does that work? No, that going here wouldn't work. Going here wouldn't work, because that would be partially negative, partially positive, partially negative, partially positive. We're looking for partially positive, partially negative. So so it'll be here. Partially positive, partially negative. So you know that I have to flip this round here. So I'd have to we can see how I have to orientate this here. This part here would have to be on top. This would be the middle. So from what I can see here, right, it would be this with this, this with this, and this with this. The only way to do that, if you saw that I was doing there, I have to flip that in shape. Remember, these are 3D molecules, so they have to flip in 3. They're obviously they're bound to the rest of the nucleotide, but be able to see that I can flip that and find it where it is there. That's what you need to look at. Where can I have the complementary? That's what you need to think about when you're doing this. Obviously, I know I'm going a bit slow for some people. They already know what I'm talking about here. But just in case, because some people haven't done A-level biology or they don't kind of know the structure of it, that's what you need to think about when you're doing these shapes. And then once you've done that, you know it's hydrogen bonding. So you get again, you don't have to do your electron cloud. If you like doing your bond like this, just showing that if you like showing a lone pair like that, that's perfectly fine. You're not going to lose marks in it, but you will lose marks if you don't show obviously going to the partially positive hydrogen and not representing the fact that it's got your delta positive and delta negative to show that they're partial charges, and also showing that this is you must use a ruler with this, right? You will lose a mark if this is not a straight line drawn with a ruler. That's what you will lose a mark there. But apart from that, and then obviously how they'll mark this, a mark for the charge, a mark probably for a straight line of some sort, obviously the overall structure, and the bond to the right one. So maybe this might be a 3 or 4 mark question, and that's how they'd go about it. Obviously the right nucleotides, obviously hydrogen bonding, and then the hydrogen bonding has straight line and charges, correct? And that's the same principle that goes to here, right? Same principle when you're thinking about it on this side here. You're looking at is it's only got two that you're really looking at here, between the nitrogen and the NH group. So we are looking at partially negative, partially positive, so then partially positive, partially negative, and then you get that here. You get that specifically here, or it depends where the thymine is responding to the rest of the nucleotide, but technically you could have that here as well. But it'd be more like this one here. Yeah, as I thought, it will be from this one. You wouldn't want to get it from reacting with here. So that's on the adenine. So that's on adenine. You would get it from here. There you go. This is the thymine here. But hopefully I'm making sense in terms of how you go about it, right? I'm getting a lot of examples here. Sometimes you might have to go for trial and error. But if you want to avoid trial and error, try and look at where it's partially positive, where it's partially negative. You already get my point now, and I'll leave you to it. But hopefully that made sense. If it didn't make sense, leave a comment in the video, and I can make a bit more sense if anything's confusing you. So DNA replication and protein synthesis rely on breaking and reforming hydrogen bonds between strands. In DNA replication, the strands separate and new strands are constructed. They're constructed anti-parallel to the old strands, and each new helix contains one new daughter strand and one new old parent strand. And in biology, we know this process as semi-conservative replication. And that's it. Hopefully this video was helpful to you, and that will be it.